This is CSAT Sample Test 4, Question 4. We're told that the parabola y equals x squared plus a quarter is eventually intersected at 2 points by the line y equals tx, where t is the time increasing linearly from 0. The question tells us that this means the line rotates from a horizontal towards a vertical position. We can see this since the gradient is increasing, t. We're asked to determine the speed at which the line segment connecting the two intersection points grows. Since we're dealing with intersection points of graphs, it might be a good idea to draw a sketch. If you haven't already, draw your own sketch first, and come back to the video when you're ready. Let's begin with our axes. What will our parabola look like? It's just our standard y equals x squared curve shifted up vertically by a quarter. So it will look like this. Then, we want to draw our line y equals tx. T is changing, so I'm going to pick a value of t that makes the intersection points easy to see on our graph, like this. And now we can see where our two intersection points are. Now we need to determine the speed at which the line segment connecting these points grows. What might be a good way to do this? Let's start by giving a name to this length, L. Then, what is the speed at which this line grows? This would be the derivative of L with respect to time. So, how can we go about finding this? We need to know L in terms of time. How can we work out the length L? Remember that we know about the x and y components of these points. And so, if we can find this length and this length, we'll call them delta x and delta y. And then which theorem can we use from delta x and delta y to find L? We want to use Pythagoras' theorem on this right angle triangle. So now we know that we need to find delta x and delta y. These come from the x and y coordinates of our intersection points. How do we find the intersection of two graphs? They're both of the form y equals something. So we can just set the somethings equal to each other. Now we've laid out a plan for how we attack this question. And we've done this by working backwards from what we want our final answer to be and thinking about how we can get there given what we know already. So now, let's carry out the working as we've discussed. First, we set x squared plus a quarter equal to tx. How can we go about finding the x coordinates of the intersection points from this? This is just a quadratic equation, so let's rearrange to get a 0 on the right hand side, subtracting our tx term from both sides. Now, there's a few different ways you could find the x coordinates, but one of the fastest is simply to use the quadratic formula. So we substitute in, our minus b becomes t, b squared is t squared, and minus 4ac, since c is a quarter, is just minus 1. And we have this all over 2. Now that we've found the x coordinates, what is our length delta x? The difference between our x coordinates. One of our x coordinates is plus root t squared minus 1 over 2, and the other one is minus. And so in fact, when we take the difference, this is just t squared minus 1. Sorry, square root t squared minus 1. Now that we found delta x, does this help us find delta y? What facts about the graph will help us find delta y? In fact, we know that they both lie on the straight line y equals tx. And so in fact, because of this, delta y is t times delta x. And so now we found both delta x and delta y. What was the next stage in our plan? Remember that we needed to find L, and we said we'd do this by Pythagoras' theorem. And so we can write L squared is delta x squared plus delta y squared, and substitute in our expressions, which gives us t squared minus 1 plus t squared times t squared minus 1, where our square roots are cancelled out by squaring, and on our delta y, the t in front of our square root also gets squared. Now, looking at this, what can we do to simplify? T squared times minus 1 gives us a minus t squared, but we have a plus t squared here, so we can cancel those. You could have expanded the brackets before doing this if you wanted. Now, our leftover terms are t to the 4 minus 1, and so L is the square root of this. Why do you think I've written it as to the power of half instead of square rooted? Remember that what we want to do is take the time derivative of L, and so it's more helpful to us to have it in this form. Which rules would you use to take the derivative of this? What we're using will actually be the chain rule. How do we apply this? First, we bring down the power. Then, we have to multiply by the derivative of the inside. Our minus 1 vanishes, and we get a 4t cubed from this term. And then, we multiply by this with our power reduced by 1. What does this look like when we write it in a normal way? Our half and our 4 cancel down to a 2, and this is 1 over the square root, t to the 4 minus 1. And so our result is 2t cubed over the square root t to the 4 minus 1. And that's our final answer for this question.